advisor and myself were both PhD students at Carnegie Mellon in the 90s, the other century, as my daughter would say. And I found out an interesting piece of information at dinner yesterday that his master's advisor is the PhD advisor of my PhD advisor. Okay, so these complex academic relations. But it's a wonderful thing to have him with us today. Mike is considered really one of the critical and leading thinkers in infrastructure, resiliency, and sustainability today. He is an assistant professor in civil, environmental, and sustainable engineering at Arizona State University, where he runs a research lab focused on studying resilience to climate change and sustainability of urban infrastructure systems. His work spans a number of infrastructure systems with an emphasis on transportation. Using stochastic models to characterize infrastructure component performance and failure trees and simulations, Chester and his students characterize the performance of infrastructure systems under extreme heat and flooding. He is co-leader of the Urban Resilience to Extremes Sustainability Research Network. This is one of the National Science Foundation research networks. It's a consortium of 10 cities across North and South America working together to develop adaptation strategies for urban infrastructure from extreme events. He maintains a body of research focused on life cycle assessment of transportation systems, and indeed, he's been one of the team of researchers that have pushed the science life cycle assessment. He's an associate editor of many journals. List some of them here: Transportation Research at GASC, Journal of Infrastructure Systems, Journal of Transportation and Engineering, and Journal of Industrial Ecology. Prior to ASU, he was a postdoctoral researcher at Lawrence Berkeley National Laboratory and the University of California, Berkeley's Institute of Transportation Studies. He got his PhD in 2008 from UC Berkeley in Civil and Environmental Engineering, and he received his master's from Carnegie Mellon in 2003. He also received a dual degree, a Bachelor of Science in Civil and Environmental Engineering and Engineering and Public Policy in 2002 from Carnegie Mellon. Please join me in welcoming Mike Chester.
Thank you all. So what I wanted to do today was talk about a hodgepodge of projects that I'm working on to give you a sense about how I'm coming at this particular problem. So I promise I won't talk about stochastic models of failure propagation unless you really want me to. I can get into that. But what I was instead going to do was give you a sense of the ways in which we're thinking about resilience, particularly in the context of the Southwest. So I do a lot of work across Los Angeles and Phoenix. I'll give you a little bit of context about Phoenix, because nobody really knows much about Phoenix. But as we discovered this morning at breakfast, Phoenix is actually about the size of Atlanta, 5.5 million people, tripling of population in Phoenix since 1990, 1.5 to over tripling. 1.5 million in 1990 to 5.5 today. When we talk about that sort of growth, we're usually talking about the developed world, but we do actually have instances of that in places like the Southwest, particularly Phoenix and Las Vegas. So it's a phenomenally interesting place to think about infrastructure, to think about transportation, because we've largely been doing this auto-centric thing that all of us know we probably shouldn't be doing. Not only that, but let's layer on top climate change. And if you want to think about climate change, Arizona, it turns out, is a really great place to do that. And I'll give you guys some of the reasons why. So what I'm going to do is talk about like I said, a hodgepodge of projects that we're doing. And what I'm really going to try to do is hit on a few ways in which we're thinking about resilience that I think we are not paying enough attention to. So you'll hear me frequently say in the next 30 or so minutes, which is what I'm going to aim for, but probably go for 40 to be realistic with you, that hardening and strengthening are typically the ways that we think about protecting infrastructure systems. And you're going to see a few different ways in which we're thinking about what resilience means and how we can deal with climate change in the Southwest. So as an academic, what we usually do when we talk about who we are, Ajo gave a very nice summary of my background, is we talk about like the projects that we work on and our credentials and things like that. But since there's a lot of graduate students here, what I anticipated What I'm going to instead give you guys a sense of is why I'm doing what I'm doing, how I came to be where I am, because I've been an assistant professor for about 6 years, and then the other stuff before that. Well, I started about 10 years ago, more than 10 years ago, as a PhD student doing transportation life cycle assessment. And I did that for my PhD, I did that as a postdoc, and then I went to ASU. So I was doing that in San Francisco, in the Bay Area, I was doing it in Los Angeles, those sorts of places that have policies around, reducing greenhouse gas emissions and understanding, to a reasonable level of precision what the greenhouse gas emissions are of doing one thing versus another. And when I went to Arizona, one, I quickly learned that there's no policies in terms of, reducing the environmental impacts of automobiles outside of your, national aviation standards and things like that. So there's not really a policy mandate to care. Two, there's no funding to do that work. There's no state DOT funding that sort of research. And I quickly realized that it was going to be really tough to continue doing that work. Around the same time, I had sort of come to this place where I said to myself, I think I've really answered the big questions in this area. Not to say that we're done with that, there may be new big questions coming up. But the questions that I wanted to answer are around things like time-based impacts of greenhouse gas emissions across the life cycle, or integrated transportation land use planning and life cycle assessment. I had done like 3 or 4 studies on each of those, and I found that, early in my faculty career, I was just sort of cranking out the next LCA. I was just pushing it through these big models that I had created, and they had 300 components of the transportation system in there, and I was just doing the next thing, and I was saying to myself, I don't really want to be doing this anymore. So I said, what should I be doing? And coming to Arizona, I realized that everything was really new, and I had been doing a lot of work in Los Angeles at the time. My wife had just moved to Los Angeles, we were apart at the time. And when I looked at the 2 cities, I said, this would be really interesting to think about why infrastructure is the way that it is. So I spent a few years doing a lot of infrastructure growth modeling, as I call it. So characterizing how the roadway network grew to be the way it is, how the rail network grew to be the way it is, how the building systems grew to be the way they are, and looking at those 2 cities because they're fairly new cities, right? They're like, you go back 100 years, there's really not all that much in LA. If you go back 50 years, there's really not all that much in Phoenix. So these are actually 2 cities where you can actually piece together the history and a reasonable amount of understanding really, really well, which might be more difficult to do in a place like New York City, where you have to go back 300 years to layer all the crazy policies and decisions that have been made over that time period to understand how infrastructure came to be the way it was. So I spent a few years sort of in this area. We did work on, for example, why the parking infrastructure in Los Angeles looks to be the way that it is, what are the parking policy regimes, and how did they come to be the way they are, and what does that mean in terms of what LA is trying to do in terms of high quality transit today and in terms of walkability and congestion. And that gave me a nice foundation to move into this space that I'm going to talk about today, which is understanding this relationship between infrastructure, how we use infrastructure, and most notably climate change and what we do about that. So that's what I'm going to talk about, and I'm going to focus on transportation. So I do a lot of work across infrastructure. Can I be a transportation person? Yeah, I can be. But can I be a power and water person if I need to be? Yeah, I can be. So we do a lot of work, which I'll get to, around the interdependencies of these systems. And I'm going to come back to this interdependency being sort of a critical aspect to how we think about resilience. Fundamentally, what am I trying to do now? I'm trying to shed light on certain concepts, one being complexity. I separate complexity and complicatedness. Complicatedness and complexity, the difference being that complexity is that we really don't understand the emergent behavior of these complex systems that we've built. Meaning that if we've layered many decisions and many types of infrastructure together to the point where if we perturb one of them, like if we push one of them with extreme heat or flooding, which I'll talk about, we don't really have a sense of how all of these infrastructure together are going to perform. You can think about like a Katrina or a Sandy type event. If we make it really, really hot in Phoenix and the power system breaks down, what's going to happen to the transport system? What's going to happen to people's mobility? Really, really complicated question. So can we model some of this stuff? Yeah. But do we really understand the emergent behavior of all of these things together? I would argue no. So we're trying to shed some light there. The interdependencies of these systems, in particular vulnerability propagation. So if I knock out power, if there's a blackout or a brownout, how does that affect a transportation system? How does vulnerability propagate through these interconnected systems? And interdependent is different than dependent. So it's that these systems rely on each other. It's not a one-way feedback, essentially. So, we've been trying to think critically about how these systems come together and what it might mean if one of them starts to go on in the chain of events that might lead to something down the line going out. And ultimately adaptation. So going back to my earlier point that so far when we look at, I would argue, when we look at what to do about climate change, it's a lot of hardening and strengthening. Let's build things bigger, let's build things stronger. And I think we're only at the tip of the iceberg there and how we should be thinking about it. Joe mentioned this. A lot of this work is going to be informed by a terrific network that I'm co-leading that is really teaching me a lot of things. 10 cities, well there's only 9 dots there. We added Mexico City recently. I was in Havana, Cuba recently trying to get them on board, which turns out to be not an easy thing to do. As a researcher in Havana, you can't just work with somebody, or in Cuba, you actually have to get permission from the country to do it. In order for the country to give you permission to do it, you actually need to have the US State Department write a letter saying that we want Cuba to collaborate, and I personally can't get the US State Department to write those sorts of letters, so that didn't come through. We have about 18 partner institutions working with us across North, Central, and South America, a wonderful group of folks. Engineers are the minority on this project, which is something that I'm not used to. It's run by ecologists and social scientists. We're thinking about urban resilience to extremes in different environments, and we are, engineers on this project are the minority. I'm leading this sort of engineering effort. So it's a very, very different dynamic than what I'm used to dealing with on projects. It's getting hotter. We can measure hotness, heat, in many different ways. I won't get into how we could characterize extreme heat, but it's getting hotter. And if you look at forecasts of extreme heat, it's particularly going to be bad in the US Southwest. So Phoenix summers are, 110 degrees Fahrenheit easy. Last summer we had a few weeks straight of 120 degrees Fahrenheit. That's what we would characterize as an extreme event. Those are forecasted under different global climate change models to, at a minimum, increase by like a factor of 3. Worst case to increase by a factor of like 10 or 12 in order of magnitude, which is essentially an entire summer at 120, 130 degrees. And as I just had a conversation with Dr. Brian Stone about, you're actually approaching the limits of what humans can actually be outside in, right? So those are pretty caustic conditions. Anybody know how many people died in Hurricane Sandy, New York City? This is an extreme climate event, right, we would say? 273. We have about 100 people per year in Phoenix that die of directly attributable heat exposure, directly. So there's indirect that's much more difficult to put numbers on. Times 12, roughly, times 10 to 12, depending on where you are in the year, is morbidity. So mortality is about 100, morbidity is about tenfold that, about 1,000 hospitalizations directly attributable to heat. So we have a Hurricane Sandy of extreme heat about every 3 to 4 years. That's not to say that one is not significant, but this is a huge public health issue. And it's not just Phoenix that we're thinking about here. Phoenix might be a great place to understand this problem, but it's also places like Las Vegas and Tucson and maybe even Los Angeles, as well as a number of other cities where acclimation tends to be a really important thing. So huge public health hazard. I just want to give you context on the heat side. Phoenix is also a pretty interesting place, Arizona, when it comes to flooding. So we don't usually think about it this way. We have a monsoon season. We actually get remnants of hurricanes that come up the Gulf of California that were in the Pacific Ocean and dump what tend to be tropical storms, they were hurricanes at one point, on the region. So between roughly June and September, we experience this sort of stuff. Flash flooding, a number of people die each year due to flash flooding. Do you guys recall about a year ago, I'll show you a picture, San Bernardino, between Phoenix and LA, you had a washout. Major bridge went out between those two cities on Interstate 10, major corridor, and cost like tens of billions of dollars in economic losses. Trucks were diverting hours, wasting fuel, labor costs, that sort of thing, and it was a significant problem. So within the context of heat and flooding, I'm going to talk about these four aspects of the transportation system, from infrastructure to accessibility to operations and ultimately interdependencies. And I'm going to talk about them within the context of a few projects that we're doing and give you guys a sense of maybe how we can think a little bit more critically about what climate change, what these more frequent events might mean in the future when we think about the transportation system as one that includes these sorts of aspects. So, flash flooding I mentioned to you. So start with 2014 in Phoenix, top right corner. That's Interstate 10, not too far from downtown Phoenix. That was a 700-year return period event. So what does that mean? So we typically design infrastructure for, does anybody know? Roughly what return period?
100 years.
Roughly 100 years, yeah. So I used to do water channel design in Pittsburgh as an environmental engineer, and I would do 100 years. So you go and you say, okay, what does a 100-year return period in Pittsburgh look like? And you look up in a table and you see, well, it has this flow rate of water and this velocity of water, those sorts of things. And those govern how you would design, for example, against scouring of a bridge, right? How much design work you need to do there and in what particular configuration. So 700-year event followed by a 400-year event within 3 weeks in downtown Phoenix. So flooded Interstate 10. A year later, you had the San Bernardino washout, bridge washout, so that was scouring. The velocity of water, I believe, so it was a 1,000-year event according to the National Weather Service, but scoured away one side of the bridge, knocked out the bridge, and Caltrans replaced that bridge within 3 weeks. So, when we talk about the ability to get infrastructure put in quickly, they impressively were able to replace that thing within 3 weeks. Matter of fact, they diverted traffic onto one bridge. So they basically brought the freeway over in the median, and then they had the thing replaced and brought back over within 3 weeks. So significant flooding issues. And one of the things that we've been asking ourselves is, how do you protect against flooding? Are the only ways to do it basically to build these infrastructure bigger and stronger? So we did some modeling work of Phoenix. We did hydrologic modeling, so the roadway network on the left, and you have watersheds that are green on the right. I have a hydrologist working for me, a graduate student, who basically simulated where flooding has happened and where flooding is going to happen. In order to do that, you have to simulate where flooding has happened. And it turns out that it's really difficult to know where flooding has happened because nobody collects this data. So where would you guys get these data? Because you have to calibrate the model, otherwise you don't know if it's accurate, right? So when we first designed the model, it actually showed us that flooding was happening nowhere where flooding was actually happening, right? So you got to calibrate it. How would you do that? No records.
Some of the experts in the agency.
You can ask the experts in the agency, which we did, and they said, yeah, about here, here, and here. Any other thoughts? It's 2017, guys.
The public crowdsourcing.
Public crowdsourcing. Specifically? Twitter. So we mined Twitter. We developed this quick and easy dirty program that basically pulled flooding events from 2014, the photos that I showed you. And it turns out you can get a lot of really good information, not only in terms of where it's flooding, like the location, but also the depth, which is really, really important. Because what is a flood? Yes, it's water in the roadway, but you can actually drive when there's like an inch of water in the road. There's actually FEMA guidelines in terms of 6 inches, 12 inches, at a certain point where basically you can't drive anymore. So we calibrated our model, basically adjusting pipe diameters and things like that, until we actually matched up historically where it's happened. And then we forced future climatological or precipitation forecasts from global climate models into that model to basically give us a sense of where flooding was possibly going to happen in the future, which is what's on the right there. From there, kind of knowing this stuff, what we've been looking at is this paradigm of what we're calling safe to fail. So I'm going to mention this sort of one time, not really jump into the details, but for the most part, what we're questioning is whether the fail-safe paradigm, which is largely how we design things, which is essentially low probability of failure, but high consequence. Think the levees around New Orleans, right? So very low probability of failure, but when they do fail, really, really high consequence. Same the San Bernardino bridge washout, that sort of thing. Versus fail-safe at the other end of the spectrum, which is this controlled failure. We allow infrastructure to fail, but when it fails, the consequences are managed, mitigated. One great example of this is what's called the Indian Bend Wash in Phoenix. In the 1960s, the U.S. Army Corps was brought in because Scottsdale, which is a major city in the metro area, was experiencing significant flooding, and it was bisecting the city. So the Army Corps designed for the city the LA Aqueduct type design, right, which I would call very much fail-safe. And the city looked at it and they said, no, we don't want this thing. It's going to bisect our city anyway if we put something like that in. So they went back to the drawing board, and this is one of the first major examples of a successful green infrastructure project, where they essentially designed 10 miles on this watershed of parks and golf courses and public space. Basically, it's entirely grade separated. That was my bike ride to campus for a long time. And it's usually just like a little trickle of water, like a foot of water going through a foot wide. But it turns into a raging river, which you can kind of see there every time we have major precipitation events. This is essentially all the water that's going to the Salt River, which is the reason why Phoenix is where it is, going back literally a few thousand years to the tribes that settled there. So, yes, you lose infrastructure when it floods. I would be biking a few days after a flood, and all of a sudden the bike path was gone. Your concrete path was just gone. So, okay, what do? You pick up your bike, you walk a block over, you go to the street, and then you continue on. Is that such a big deal? Not really. There are costs to that. The city would come in within a few days, they would put a new pad of concrete down. It wasn't such a big deal. They would replace certain things that had broke. But this is a nice example of safe to fail. So we've been thinking about more critically what safe to fail versus fail safe means. And in the literature, there's almost nothing. Safe to fail is defined as the antithesis of fail safe. Whatever fail-safe is, it's the opposite. So I've got a PhD student who has been sort of thinking about the characteristics of resilience and how those apply in a spectrum between fail-safe, safe-to-fail, and basically saying the confluence of certain variables, certain characteristics over here versus over here might be more fail-safe versus